So welcome to CSP for Complexity session. We're on a nice schedule, so I'll ask the speakers to stick to the time, 15 minutes. Our first talk is by Kunal. He's going to tell us about approach to parallel repetition via CSP inverse theorems.
Hi, thank you for coming here to my talk. I'm going to be talking about an analytical approach to parallel repetition via CSP inverse theorems. And this is joint work with Amey Bangle, Mark Braverman, Suhas Khote, Yang P. Liu, and Dor Minzer. So throughout the talk, if you have any clarifying questions, please feel free to ask me. And I'll try to keep it like not very technical. So before I get into what each of the terms in the title means, first I need to define what are called multiplayer games, which are very crucial to the topic of parallel repetition. And I think the best way to define it is to give you like a concrete example of a multiplayer game, which is the anti-correlation game. So this game was introduced by Feige in like a blog post on his website. So the post is called Test Your Telepathic Skills. And in this game, essentially what is happening is a group of three magicians are like playing some game and they're doing something like which people think is telepathy, but actually what they're doing is just what is parallel repetition. So let me try to introduce what the game is. So the game has three players, which we denote as P1, P2, and P3. So the game starts as the following. So there's a verifier. What the verifier does is the verifier samples 3 bits, X, Y, and Z. So they're chosen uniformly at random such that 2 of them are 0 and 1 of them is 1. And like among the 3 possibilities, you choose each of them with probability 1/3. So the verifier gives X to the first player, Y to the second player, and Z to the third player. And now the players are required to give back bits as answers based on the inputs they get. So for example, the first player answers A, which is like a function of X, the second gives B, the third gives C. And finally, the verifier gets all of these X, Y, Z, and ABC from the players. And the verifier says that the players win or lose. And to say this, the verifier evaluates some function of X, Y, Z, ABC. So for example, here the function is that the 2 players who get input 0 must output different answers. So for example, if the input was 0, 0, 1, then we require the first 2 players to output different answers. That is A not equal to B. And the quantity we'll be interested in is what is called the value of the game, which we denote as value, val g, and that is the maximum probability with which the players win. And the maximum is over the choice of these 3 functions f, g, and h, and the probability is over sampling these x, y, and z from like this set I just showed before. And so I'll just say something very simple. It's very simple to prove that the value of this game is 2/3 exactly. So let me just say, so how do we prove that the value is at least 2/3? Suppose the first player always answers 0, and the second and third players always answer 1. So then consider, for example, this input 0, 0, 1. In this case, A not equal to B is satisfied, so they win. And similarly, they'll win like all of the 3 inputs except the one which is, for example, in this case, they'll lose on 1, 0, 0 because the input to the second and third player is being compared. And it's like a very simple exercise that they cannot do better than 2/3 in this case. Okay, so now based on this example, I will just define what multiplayer games are in general. So even for multiplayer games, I will define what a 3-player game is. It's exactly the same. So you have 3 players, P1, P2, P3. The verifier now samples X, Y, Z from some arbitrary distribution over 3 inputs. Let's call it mu. X, Y, and Z are given to the 3 players. They give back some answers, A, B, and C. None of these are like required to be bits now, as in the previous example. And now you have like some arbitrary win condition V on X, Y, Z, A, B, C. And again, you have the same value of the game. So the value is the max over the functions f, g, h of the probability of winning. Okay, so this is a typo. F, g, and h may not be from 0, 1 to 0, 1. They are like from arbitrary sets of the first input to the first output and so on. And I will also make like a small remark. So using public and private randomness in these functions f, g, and h does not help the players. So you could, for example, just fix some best randomness and you can get the same value. And similar to this example of 3-player games, you can also define k-player games. So multiplayer games are like very important. So for example, 2-player games have shown up like in PCPs and things like this. For example, like the PCP theorem is essentially equivalent to saying that it's hard to distinguish whether a two-player game has value 1 or 1 minus epsilon. And now in many of these applications, what happens is that this gap of 1 and 1 minus epsilon, you want to boost it to something like 1 and epsilon. And you want to do it while maintaining this one round feature of this game. So for example, the verifier just gives something to the players and just gets something back. It's like one round. So the natural approach to do it is what is called parallel repetition. So given a three-player game G, which I just write on the left, I'll define what is called like the game G to the n, which is the n-fold parallel repetition of this game. So what happens is that the players are trying to play n copies of the game in parallel. So what the verifier will do, the verifier will now sample xyz from mu, and the verifier will sample n copies of these independently. So we'll denote them by xi, yi, zi. So the first player will get all of the x's, x1 up till xn. The second player will get all of y1 up till yn, and the third player will get all of z1 up till zn. And now the first player is required to answer back n answers, a1 up till an, the second player will give back b1 up till bn, and so on. And we say that the players win if they win all n copies of the game. That is, for every I want the win condition v to be 1 on xi, yi, zi, ai, bi, ci. And the value of this new game is what is we denoted by value of g to the n. So I'll just note a subtle point that because the game is being played in parallel, all of the outputs of the players, a1 up till an, can depend on all of the inputs they get, x1 up till xn. Okay, so let me just say what is, so it is natural to ask, what can we say about the value of g to the n if we know something about the value of g? So it is easy to see that the value of g to the n is at least the value of g to the power n. So the players can just use the independent strategy that attains value val g in each of the n coordinates, and they get value val g to the n. So also it is easy to see that the value of g to the n is equal to value of g to the power n. So this is just because the inputs to the players were sampled independently. And while one is very tempted to say that this obviously is true, it turns out that this is false. And so in fact, some of the earlier papers even like claim this to be true. And there are very simple counterexamples. You can show that there are games where value of g to the n is much higher than value of g to the power n. So for example, it's an exercise, it's not too hard. So you can show that for the anti-correlation game I just showed, if you repeat it 3 times, you can get the same value. And this is what like Feige called telepathy in his example. And what this also shows is that the value of g to the n is at least value 2 over 3 to the n over 3. So the reason is that the players can play this strategy for 3 copies of the game, like you can divide n in blocks of 3 and do this. So it's like not something just about 3. You can get like asymptotically better by just doing better on like a small set. But now you might still ask what is known about parallel repetition. It is like well studied and like there are a lot of papers on this. So Nanras proved in the 90s that for 2-player games, when the value of g is less than 1, then the value of g to the n decays exponentially in n. And for most applications like PCPs and hardness of approximation, this is like good enough. But for multiplayer games, the situation is like very grim. Essentially, the best result we know for any k-player game where k is at least 3, like for the general case, is that if the value of the game is less than 1, then as n tends to infinity, the value of g to the n goes to 0. And the decay bound is like something horrible. It's something like 1 over some inverse Ackermann function. And this comes from this black box use of something called the density Hilscher theorem. And so there has been a lot of recent work in which like better decay bounds are known for special classes of multiplayer games. And so one interesting thing I would say about these classes is that, so these papers I would say have like 6 to 8 different proofs, all of which look like very different and in some sense also use like very different techniques. And they prove it for like different classes of games. And like there is no like unified approach to like saying like what is common among these different proofs. And just as an example, I would say that, for example, we know exponential decay for the anti-correlation game I just showed. And so before I move to our results, I will also like just generally mention some applications. So the 2-player case of parallel repetition since the 90s has found a lot of application. For example, in PCPs and hardness of approximation, in like how you can tile the space using like some weird tiling bodies in quantum information, communication complexity, and so on. So the case of multiplayer games with like at least 3 also has some potential applications. So none of these have been like realized yet. So for example, we know that strong parallel repetition for a very, very special class of games would imply superlinear lower bounds for non-uniform Turing machines, which is like a very classical open problem. And also we know that when answer sizes in like these games are allowed to be like very large, say even infinite, these are like equivalent to problems in additive and extremal combinatorics, like very central problems. So for example, something called the GHZ game, which I won't go into what it is the same as like the density of square free sets in f2 to the n cross f2 to the n, which is like a very central problem. And also we hope that techniques that we use to develop parallel repetition can be used to prove like sum and product theorems for number on Fourier communication complexity, which also implies like circuit lower bounds. So there is like good motivation to studying these games. Yeah. So I'll first start by describing what our main result in this paper is. So we prove the following. So suppose G is any game which is pairwise connected. I'll get into what this is, and such that the value of G is less than 1, and suppose G is a 3-player game, then the value of G to the n is at most 1 divided by log 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 n, where the number of logs is maybe you can think of it as 10. So we don't explicitly calculate what it is, but it is like an explicit constant, like probably 10 works. Okay, so let me just say what this pairwise connected condition here is. So what I want is that the marginal of the query distribution on any 2 players is connected. So I will construct this graph. So consider the first 2 players. I will consider this graph which has edges as all the possible pairs of inputs to the first player, which is like all x comma y, so that there is some completion to some input in the support. And I want this to be a connected graph. So let me give you an example. So suppose I have the anti-correlation game. So this was the support of like the input distribution. So if I consider the first 2 players, the possible inputs are 1, 0, 0, 1, and 0, 0. So you get this graph, and this is a connected graph. So for example, our theorem implies like this particular bound for the anti-correlation game as well. And we also have like a more general k-player version of the theorem, so I won't go into what it is. Like it says that instead of pairwise connected, you get this complicated condition saying that no marginal on k minus 1 players admits something called a non-trivial embedding, and the number of logs you get depends on the number of players. Yeah. So the main result we also get, I think, like just other than the proof this pairwise connected is also that I think we get like a new analytic framework which proves this. And this new framework also recovers every previous parallel repetition result that is known. Like via these 6 to 8 different proofs, it gives like a unified approach, although with like weaker bounds. So for example, it gives a completely new proof of 2-player parallel repetition. It gives a new proof for connected games, for something called player-wise connected games, for 3-player games with binary inputs, and also for like certain 3 XOR games. Yeah.
So how does the value of the parallel repetition depend on the value of G?
Yeah, so I think we just think the value of G is some constant less than 1. We don't care how. So we just think of it as some constant. So the dependence on the value will be like very bad. Yeah, so we don't explicitly analyze it here. Yeah. So like maybe in the last 2-3 minutes, I will just say like one slide about like how we do things. So the main technical ingredient that goes into it is what is called like a CSP inverse theorem. And this was, so the setting is the following. Suppose mu is any distribution on 0, 1, cross 0, 1, cross 0, 1. In general, like over arbitrary sigma 1, sigma 2, sigma 3. And suppose f, g, h are functions from 0, 1 to the n to like minus 1, 1. And I want to understand when is the following condition true. That if I take the expectation of fx, g of y, h of z, where x, y, is the n sampled from like the n-fold repetition of mu, when is this like approximately like a product distribution? Like when do these behave approximately in a product way? And a recent line of work by Bungley, Cote, Liu, and Minzer like answered this question, when mu is a pairwise connected distribution. So they say that if mu is a pairwise connected distribution, and all of f, g, and h do not correlate with something called a low degree function times a product function, then this condition holds. So I won't go into like the explicit definitions. I'll give an example. So for example, if your function looks like some function of the first 7 variables, which is like a low degree function, times it depends on like some function of x8, x9, x10, and so on. This is like a product function. And like these works also develop like new notions of like random restrictions to deal with it. I won't go into it. And this also led to like a recent breakthrough in like this problem of three-term density Hills-Jewett theorem. Yeah, so in the end, I'll just like, yeah, again display my theorem and like some potential future directions. So one thing I want to say is that this pairwise connectivity somehow seems important for these CSP inverse theorems, but there is like no real barrier to prove parallel repetition. So I think it is completely plausible that with the current techniques, we can just prove parallel repetition for all 3-player games. So also, can we prove improved bounds? For example, using like this technique, can we get exponential bounds for 2-player games? And also, yeah, are there other applications of these techniques? Maybe in additive combinatorics and communication complexity. Okay, yeah, thank you for listening.
Do we have time for questions? Any questions?
How important is the distribution? Can I just assume like uniform?
So technically, the way I think things work is the sparser the distribution is, the harder it becomes. So for example, if the distribution is everything, like then it is very easy to prove such results. So pairwise connected is in a way like classifying how connected it should be, like how many points at least you need to have in the distribution.
Suppose you have a distribution which is not pairwise connected. Now, can you just add some points in the support with very small probability and use this theory?
So suppose you get this new game which is G prime.
Yeah.
So you can say that the value of G prime is less than 1,
Yeah.
but it is unclear how the value of G prime to the n says anything about the value of G to the n.
Oh, but the extra points are coming with very low probability.
Yeah, but like when you repeat it n times, like you sample a lot of them. Yeah.
N goes to infinity.
Yeah. Any other questions?
Let's thank the speaker again.